Alright, so are we ready to tackle electrochemistry?
Yes, let's do it.
Let's do it, okay. Now, what we are going to do today is just an introductory lesson, those that are listening, on what we call galvanic cells and electrolytic cells. But it's under a general heading. In our textbook, this is called electrochemical cells. Yes, you could call it electrochemistry, okay, as well. So they're both called electrochemical cells. There are two types of electrochemical cells that we're going to study. The first type is called a galvanic cell, and as you can see on the board, they are also called voltaic cells. The reason is they produce a voltage. They're a battery. Okay? So although this does not look, how I've drawn it here, doesn't look anything like a nice package in terms of a dry cell battery, okay, there is, within this, two electrodes. And the electrodes are the actual container. So the actual outside of this battery is a zinc electrode, okay? At the top of it, insulated, that green little circle there, insulates the other electrode from the zinc electrode. In the middle, underneath that stainless steel cap, is a carbon electrode. In the middle, between the carbon electrode in the middle and the zinc coating, there is an electrolyte, like a salt bridge, okay? But nothing is happening in here at the moment until I close the circuit and I turn on the switch. Then the chemistry goes to work in here, okay? So nothing will happen in a battery until I close the circuit, okay? That's the thing to remember, all right? So this is the battery in our picture. This is the load in the circuit. Mobile phone, radio, whatever, okay? But this is the battery that we use to power, all right, power the system. That's a galvanic cell. So what we're doing in the context of the galvanic cell is we are changing chemical energy into electrical energy. So what reaction are we using to our advantage here? We're using redox, okay. So we did a few weeks on a redox reaction. So we are using redox, okay, because redox involves transfer of electrons. Now electrons don't move in a solution, okay, in this instance. The electrons are moving in a copper wire in an external circuit, okay. When I turn the switch on, and when the circuit is closed, and when the salt bridge is also active, that brings the two half cells together. When we do galvanic cells, we have to remember, I'm recording, that's all. When we do galvanic cells, we've got to remember three things, okay? And they are oxidation, anode, negative. So in a minute, when I tell you to go write this down, you're going to attach that to your memory for galvanic cell. So when we're doing galvanic cells, it's the first thing you have to remember. Oxidation, anode, negative. When we look at electrolytic cells in more detail, you're going to remember oxidation, anode, and positive. That goes with an electrolytic cell. Okay? So they're the two things we have to associate with different cells. Back to our galvanic cell. In the galvanic cell, as we just did when we did activity series of metals, we now have got the two metals separated. This is called a half cell. How do we work it out? Because together, if I join my half cells together, they form a cell. Here's a cell. This is a battery. Okay? But they are actually made up of two halves. And funny enough, one of the halves is going to undergo oxidation, and one of the halves is going to undergo reduction. Okay? So we actually physically separated out our oxidizing agent and our reducing agent. In our little test tubes that we did last lesson, here we had the metal sitting inside of the metal solution. And of course they weren't separated, so all the reaction was happening inside our flask. okay, inside of our test tube. So what we've actually done now is we've separated the two metals, put them in solutions of their own metallic salt, and now we go back to the activity series of metals, and that allows us to work out which of these two metals is the most reactive. Now, if I'm looking at just zinc and copper on the activity series, which of those two metals is the most reactive? The zinc. Here it is over here, where it is. Zinc. Zinc's here, copper's way down here. So zinc is the most reactive metal, and here's the hard part. For every metal combination that we're using, the first thing is to work out which is the most active metal. That's easy. And you told me it was zinc. Okay? The cell reaction for this can be one of two. We can end up with this. Zinc plus Cu2 plus, because we've got a zinc electrode here. Or we could have copper plus Zn2 plus, because I've also got a copper electrode over here. So what I'm trying to ask you is, does zinc react in preference to copper, or does copper react in preference to zinc? Which of the two is the most active metal? And you would tell me which one. It's the zinc, okay? So this is the one that's going to react, because you know that the zinc, M, is above N on the activity series. You told me that, okay, in the previous lesson. Now, just kill that. That helps me because on this half cell, where all the zinc sits, I can work out what the reaction is for this half cell now. Okay? So I had to actually work that out by first of all going back to the activity series of metals. So this half cell, I can write the reaction. This half cell is going to be zinc must go to Zn2 plus 2 electrons, because zinc, here it is, zinc is what's reacting, okay, in this half cell. It's more active. Omar.
So the one on the left is the one that has a preference, or is it the one?
No. Okay. If not the cell on the left.
No, I'm talking about in the equation at the bottom. Which one's got preference?
The highest one between the two metals is going to be the most reactive.
Oh.
The highest one in the activity series. Okay? When you said the one to the left, it might not be the left-hand cell, it might be the right-hand cell. It depends on how I draw it.
Yeah.
So I could have flipped this around and had zinc on this side and copper on this side. So don't assume that every left-hand cell of a dual cell battery is going to be the most active, because it won't be.
Yeah.
Okay? There is a convention about that, but we'll look at that a little bit later. Okay? Alright, so zinc is the one that's going to react. So I had to work out what the combinations of metal ions could be. But notice that it's a metal in the same metal, and the metal in the same metal ion. Okay, we've got those things physically separated. Now, we've worked out that that's the reaction. So that means if that's what's happening in this half cell, then I can work out what's happening in that one. So that means it must be Cu2 plus aqueous plus 2 electrons goes to copper solid. So they must be my half cell reactions. Okay. If I add those two half cells together, like I would for a normal redox reaction, I get this. That plus 2 electrons goes to Cu solid. That's aqueous. The overall cell reaction for this battery would be Zn solid plus Cu2 plus aqueous goes to copper solid. Going to cancel those, okay? Just typical redox addition, plus Zn2 plus aqueous. That would be the overall cell reaction, okay, if I were going to add them both together. I'm going to get rid of that one now, so I don't need it there, okay? But that's the overall cell reaction, based on the fact that zinc is more reactive than copper. Zinc is behaving as what in this instance? A reducing agent or an oxidizing agent? As a reducing agent. Okay, that means this half cell is undergoing oxidation. Thanks, Gordon. This one is oxidation. So this is my oxidation half cell. Okay, and I'll show you how we use this to work out everything else that we need to know about a galvanic cell. So this is my oxidation half cell. That means this must be my reduction half cell, and of course it is, because it's gaining electrons. Now, then I go to my little acronym, oxidation anode negative. If this is the oxidation half cell, that means this is the anode in the system. Okay? Oxidation anode. That means on the surface of the zinc, it's going to have a negative charge. Can everybody see why the surface of the zinc is going to have a negative charge? Okay, be honest. Alright, so Param said he doesn't get it. What's happening with the zinc is this. The zinc is dissolving into solution to form Zn2 plus ions. Here's our reaction. It's leaving behind 2 electrons every time a zinc does that. Okay? Another zinc goes into the solution. That's 2 electrons left behind. Okay? And eventually the whole electrode obviously is going to become negatively charged because the reaction tells me that. Alright? It's leaving behind the electrons as the zinc is being dissolved. So that electrode over time will disappear, or every part of it that's in contact with the zinc ions will disappear. Okay? That's why batteries don't last forever, by the way, because eventually the materials that are used in the batteries, if it's a dry cell battery, eventually they corrode. We can't replace them. Alright? We'll talk more about that later as well. Alright, so that zinc anode over time corrodes, but while it's corroding it leaves behind electrons such a negative charge. So, if this is copper wire in the outside, nothing to do with this copper, it's just a conductor in the outside, knowing what moves in wires, what moves in a wire? Electrons. Okay? So if I hook up a piece of wire to a negative terminal, it's going to repel. Electrons will repel one another. Okay? So the electrons will flow from the anode in the external wire to the cathode. Okay? And funny enough, alright, over here, if this is a negatively charged, oxidation anode negative, that means the cathode is positive, and of course positive attracts negative. It attracts electrons. So it just makes sense that electrons are going to flow the way that I've got it, from the most active metal to the least active metal, in any circuit that I make, all the time. Okay? That's the driving force though. The driving force is activity series of metals, and it's the redox reaction, physics separating the 2 metals. The most active metals will move its electrons to the least active. All we're doing is, we're just utilising the electron flow, and like I said, it will only happen when I close the circuit. And of course, I'm not a very good conductor, alright? But if it's a piece of wire going from here to here, with a globe in it, you would see the globe light up. Current.
So, now you said the zinc metal becomes a zinc ion and 2 electrons.
Yep.
Does that mean it just like dissolves?
Yeah. The equation says zinc solid goes to zinc aqueous.
So it just dissolves?
It dissolves. So this solution here is getting lots and lots of Zn2 plus over time.
And so the 2E that goes to the
Yeah.
That travels over to the least reactive metal.
Correct. That's what happens. Alright, and all we're doing is, nothing will happen of course if that's open. It has to be a closed circuit. Alright, and as soon as I turn a switch on in the circuit, then it works. Okay, those 2 metals are reacting with one another external to the load in a battery. Okay? External. Separate to the battery. No.
If batteries, does that mean the most reactive metal is the reducing agent?
Yeah, all the time. Yeah. The most reactive metal is the reducing agent, which is the oxidation.
Yeah.
For example, okay, in this one here, alright, we look at it, negative, this is a battery, negative, positive, okay. The negative is the zinc in this case. Funny about that, isn't it? zinc negative, but in the battery, in this dry cell battery, the actual the cathode over here, anode, cathode should label it, but the cathode is carbon in this instance. It's not a metal. So it's zinc carbon in a battery, but zinc's higher than carbon on the activity series of metals. But the problem is that carbon is not on the activity series of metals because it ain't a metal, just a conductor. Okay? So any metal we could have on that is going to work, in theory. But we don't want it to be too corrosive, otherwise it's going to leak the alkali electrolyte out, which sometimes does. And people call that acid, by the way, don't they? Like acid. If it's a battery, like a car battery, yes, it is acid, but 99% of the time, if it's a dry cell battery, it's alkali. It's not acid, it's actually a very strong alkali. All right, anode, cathode, in this instance here, we need to label that cathode. And that's a system, almost, of our battery. The other thing is, you will always ask in the salt bridge, which direction the ions move in the salt bridge. This says KCl aqueous. It's just a salt dissolved in solution. So I'm going to have potassium ions, and I'm going to have chloride ions that are in this piece of paper that's just been soaked and draped over 2 beakers. Which direction are the negative ions going to flow? Any ideas? And why? Who thinks the negative ions are going to flow this way? Who thinks it's going to flow that way? Okay. The first people won. They go in this direction. So put up your hand if you said the negative ions are going to go in that direction. Okay, Abdul, why?
Because on the other side, the electrons are going from the zinc to the copper, and from the copper is going to go to the zinc.
Okay, so he's got the right idea. He said that in the circuit, the electrons are flowing in that direction. Okay, this is a way to work it out. Things that are negative in the salt bridge are going to flow in the same direction. Alright? So electrons are flowing away from this. Okay, so that means things that are negative are going to go in that direction, in the salt bridge. Remember, these are not ions, so these are not electrons, there's ions moving in the salt bridge. The other thing to remember is, in the solution here, what's happening to the charge in that solution over time? It's going to increase. More positive. What does positive attract? Negative. So the chloride is really there to try and neutralise the charge in that half cell. Okay? Everybody got that? Alright. Over here, obviously, if the chloride flows that way, the potassium ions are going to flow in the opposite direction. Why? What happens over here? What's happening in this half cell? The reaction says that the copper is plating onto that electrode. Cu2 plus goes to copper. So we're plating copper onto that electrode. That means these are getting lost, they're being taken out of the solution. This side then is going to become more negative because I've got still NO3 minus there, or chlorides. So this potassium is going to try and come down and neutralise the negative. It's a very complex process that's happening in each of the half cells. But it's all based on, I hope you can see logic. Positive attracts negative, negative repels negative, okay? The most active loses electrons towards least active in terms of the metals. Oxidation, anode, negative. They're all things you have to actually commit to memory and understand. Okay.
We do have a practical where we actually see this happen.
Yeah, we'll be doing it practical later on. Yeah, and I've got a few videos in the sector as well that you can look at. All right, Omar. What's happening to the Cl minus? The Cl minus is simply moving, okay, from this area in the salt bridge to the zinc anode. Yeah, it's moving. It will move eventually. What's going to happen over time with the salt bridge? It's going to, no, the salt bridge won't dissolve. But unless I keep on topping up the salt bridge, I like taking the salt bridge out, putting more potassium chloride in it, putting it back again. It's going to eventually get all the potassiums on that side and all the chlorides on that side, it'll stop working. That's why batteries don't last forever. Okay? What's going to happen in this side of the half cell with the zinc eventually? It's going to dissolve. If the zinc dissolves, no battery, no electrode. Okay?
What happens to rechargeable batteries?
We'll get to that later, Param. Okay? But rechargeable batteries, hopefully you can think about rechargeable batteries, are not going to have electrodes over time that are going to corrode. And a rechargeable battery means we can reverse the reactions. These reactions here, once they occur, they're not reversible. So a rechargeable battery means you've got to be able to reverse these reactions, but when I do that, I actually turn it into an electrolytic cell. That's a few lessons down the track. Omar?
Is the only reason why the scoring goes that way is because it loses charge, and it's losing charge as the electrons are
No, the reason why the chlorine goes from right to left is it's trying to bounce out the positive in this half cell.
So it's attracted by the zinc.
It's attracted by the Zn plus 2 in that cell.
one of the electrons on that side.
Yes. And the way to think about it is everything negative in the circuit has to flow in the same direction, you know? You can't just have positives and negatives flowing in opposite directions. It doesn't satisfy conventional current. Okay? Now, last thing. The electrolytic cell, alright, is again basically turning electrical into chemical energy. That's what happens in an electrolytic cell. So I need a battery to make this work. Where does the battery come from? Believe it or not, okay, this could be a galvanic cell. That's my battery, okay? So I'm actually using a battery, okay, in this instance, there's my battery, to generate a chemical reaction. Because this reaction, whatever I'm trying to do in here, is not spontaneous. I didn't use that word yet. It's not spontaneous. I need to push electrons into the system to make it to work. How do I push electrons around a circuit? With a battery. What makes electrons move in a circuit in a battery? Redox reactions. Okay? So they all connect, more or less. Okay? In this one here, the way to remember the charge, okay, on the electrodes is the long side has got, you've got to use more ink for that. So that's always the positive side of a battery, and the short side is always negative. Okay? But it's the opposite for an electrolytic cell. The anode is positive. Okay? All the time. So it's not positive because the reaction is going on there. It's positive because it's hooked up to the positive side of a battery. There's a difference. This one over here was positive, okay, because it was undergoing reduction in that half cell. That's what caused it to be positive. This one is positive because I hooked it up to the positive side of a battery. Big difference between the two. So this one here, I'm going to put positive there and negative there because they're hooked up to that side of the battery. Okay? I'm not worried about the direction of electron flow here in this circuit, it doesn't matter. But we know it's going to be in that direction if we were asked. Or is it? We'll work it out in a minute, won't we? Okay. This one here, anode, so this must be the anode of the circuit then. Anode, oxidation, positive. This is the cathode, okay, of the circuit. Oxidation, anode, positive. Oxidation, anode, positive, just checking. Alright? That must be the cathode. Now the anode is the positive, the cathode is the negative in our circuit. Okay? What we've got here is water, okay, at the anode is going to produce oxygen. Okay? Water reacting at the cathode here is going to produce hydrogen. And now I'm just going to balance the half equations. So I need to have a 2 there. That will be 2H plus 2 electrons. This one here, I've got to balance the oxygen by adding water. So it must be H2 over there. I need 2 of those. How do I balance the rest of it? What else do I need? I've got 4, 4. What else do I need to balance that reaction? We need electrons here. Balance the hydrogens. 2, 4. That's a bit weird, isn't it? Let's do that again. Okay. So H2O goes to H2. Oh, yeah. Plus H2O. I was a bit too quick. 2H plus plus. That's more like it. Okay. 2 electrons. All right. So, what sort of a reaction is it that's occurring in the anode? Is it oxidation or reduction? It's oxidation, isn't it? Okay. This is loss of electrons. This is the oxidation. This is where reduction is occurring. Okay. So, in the case of an electrolytic cell, all right, we work with electrolytic cell slightly differently. We know which one is the anode from the charge. We know which one is the cathode from the charge. So, which way are electrons flowing in the circuit then? Look at the reactions. Where are the electrons being gained? Clockwise. Here's our reaction. Look, plus electrons. So yes, they're going in this direction. It's the negative side of a battery. That means electrons are going like there, okay, in order to react. Well, they're not going into solution, but they're on the surface of that electrode because it's hooked up with the negative side electrode. Okay. Now, there's a lot in that, like 20 minutes or so we went through all that. But there are lots and lots of concepts in there just to introduce you to that. Okay? Any questions before you copy this down, Natalie? Param? Yep.
You've got those equations, I'm not sure where you got them from.
Where?
I know you use the H plus and H word, but...
Yep, what I've got here in this solution is a weak acid solution. That's why I had to have H plus for it to be a conductor. Water reacts at both the anode and the cathode. One thing I forgot to mention was, you also have to remember oxy anode. And that tells me, if nothing else, in an electrolytic cell, if I've got lots of water present, I'm always going to get oxygen at the anode. Just an electrolysis of water. If I break water apart, I get oxygen, and I get carbon. That's what I'm doing. One is oxidation, one is reduction. The driving force is the battery.
You start off with the equation, you start off with water.
Yep.
The conjugate of water is
Oxygen. Okay. I think your question is saying, how did I know that I'm going to get oxygen?
Yeah.
And how did I know that I'm going to get hydrogen? Okay, because I've already looked it up. I've gone to the table of oxidizing agents and reducing agents. And I know that when I carry out electrolysis of water, I'm going to get oxygen and hydrogen. All I had to know is which electrode I'm going to get which gas. Okay? So I actually had to know that. I had to know the products before I did the reaction. Okay? In this cell, it's not so fussy because I already knew what they're going to be. It's going to be either metal ion or the metal. They're going to be the products. Okay, Sina.
What's the function of an electrolytic cell?
What do we use the electrolytic cell for? I'm pleased you asked. Okay, now, let's think about it. So, we use, well, the function of this, hopefully you've got, is a battery, yeah? Now, there are two types of battery. We call batteries primary cell, and we call them secondary cell. The secondary cell batteries are rechargeable. Okay? So there's a whole series of stuff on batteries. Like these ones now, what are the ones in the phones? Lithium, okay? Lithium ions or not?
Yeah, lithium ion.
Okay. So the lithium ion is a rechargeable battery. I can reverse the reaction, I can use it again. Okay? Dominoes, midweek. I hate that.
Too.
Do you get that too?
Yeah,
Oh, I don't know where that comes from, but anyway, I've got my mobile number. So there's lithium ion batteries, okay? Now, batteries, are also primary cells. This is a primary cell. Of course, I couldn't use it in here. It's not going to power my phone, or it will for a little while, but primary cells are not very effective over time because primary cells, they just go from the time I start using it, the current goes like this. It just goes down and down and down and down and down. Okay? But the technology used for lithium ion, okay, in a phone, it'll hold a voltage for a long period of time, then all of a sudden, it'll tell you it's flat, phone's off. It turns off when it's 0, okay? But it will maintain a voltage for a long period of time because it's a piece of, high technology. It needs the current for the whole period of time. That's a primary cell, secondary cell. Over here, electroplating, which we'll do in class. Electroplating, okay? We've got examples like in the lab, okay? So, if we look at just a chrome tap, okay, like this thing here. So this has been chrome plated, all right? Underneath that is probably steel. It may have been copper, I'm not sure, okay? Most likely copper, but certainly it's been chrome plated. So that means it would have had to be dipped in a solution of chromium ions. Which electrode gets plated? The positive electrode or the negative electrode? The negative electrode, good. Because chromium ions have got positive charge, they're going to go to the negative electrode. Cr plus 3 electrons goes to Cr, chromium solid. It's that simple. So that's being plated with chrome. Okay? And we like that because it's shiny and it's attractive. Okay? Another reason or another system you may have seen or heard of with aluminium, and I haven't got any of it on me today, but for those of you who maybe have like push bikes, like bicycles, or a lot of the racing gear these days, like motorbikes and road racing stuff, they use anodizing. Now, anodizing is where we take aluminium, okay, we coat the aluminium with a dye, and it makes it nice, because it's colourful, but it is also resistant to corrosion. Alright? And that's anodizing. Another process is called galvanizing. Not so common. Okay? But that's adding zinc to the surface, okay, of steel to stop it from corroding, because zinc's more active than iron. The zinc corrodes in preference to iron. It's more redox there. And just the whole chemistry involved in corrosion protection. So there's a lot of money in trying to stop iron from rusting. Okay? A lot of money involved in that. Alright? Now, if you understand this stuff, you can understand the chemistry associated with that. Okay? Another example of where we use activity series of metals. Has anybody got outboard, anybody got parents with outboard motors? An outboard, like a motor on the back of a boat? Anybody got outboards? No? Okay. Most outboard motors are enamel coated, or they're anodized, and somewhere on the motor they've got a block of zinc that sits on the motor. Why do you think they've got a block of zinc that sits on the motor that sits in seawater all the time? Obviously the seawater's salting, it's a great electrolyte. Okay, but why have they got a block of zinc in contact with quite often steel motor? Because where's zinc on the activity series of metals? Here's zinc. Where's iron? Underneath it. So if I've got zinc and iron in contact, which is going to corrode first? The zinc. The iron will stay safe. Okay? All the metal ships, you don't see them, but below the surface, the waterline of all these ships, they've got massive zinc blocks. Okay? They are attached to the hull of a ship. And they've got to be replaced over time. Because as they corrode, if they don't replace the zinc, okay, the iron will obviously increase its rate of corrosion significantly. Think of it as sitting in salt water all day, every day. Okay, it's got air, oxygen from all the waves around it. It's a perfect environment for corrosion. Put zinc against it, the zinc will corrode in preference to the iron. Okay? That's where the chemistry comes in. Omar?
You can't paint with potassium.
No, you could, Okay, the problem is, that's a nice thought, okay, if I slap a piece of potassium on the boat, okay, within about 30 seconds it would have dissolved. And probably exploded and put a hole inside the boat as well. Okay? So it can't be so reactive that it's going to disappear like that. Okay? You have to understand that, alright? So, but it's got to be above whatever metal you're trying to protect on the activity series. But we don't need to worry about things like copper, silver, gold and platinum because they don't corrode. They're the most stable metals on the activity series. So can you see where the chemistry is going with this? It's probably more than what I wanted to do, but that's where this is used. Okay? Everybody cool? All right, out of here.